Leave the land of the precise and go into the absurd. So, all right. Hey, I'm making a career out of this now. So, let's put it this way. You've heard of the PACE mission. We basically are selling this mission on the ability to do this. This is why we're getting a new mission. And so in my role as a project scientist there, I spend a lot of time trying to convince people, whether I believe it or not, particularly manager types, that this is important. So you find yourself in the position of cheerleading a little bit. And you're talking all different kind of audiences, and you're talking to newspaper people and stuff like that. And so even though you know all this, I'm just going to share with you how I found myself starting to introduce this concept to people who have no concern whatsoever whether phytoplankton live or die. So I've been starting them off with a questionnaire. I'll ask you this question too. Do you like breathing? Do you like eating? Then you care about phytoplankton. Because what we're trying to do here is linking, you know, why somebody who lives so far away from the ocean should actually give a shit about this kind of stuff. Why this is important. Why we should invest $800 million in missions satellite missions to be able to detect this from space. And so everybody in here knows this, but these are the answers that we then show to our audience who is now convinced they want to be a phytoplankton ecologist. And then you can go on and talk about the significance of this in terms of where phytoplankton come in the global carbon cycle and our changing climate and our rising CO2 lecture. So this is the fun fact number 2 that I usually impose upon the audience and describe that this is a really, really big number and that phytoplankton play a big role in sequestering carbon dioxide from the atmosphere into the deep, deep, deep ocean. The best graphic I have for this, which I don't have as part of this presentation, but keep it in your back pocket, is nobody knows what 40 billions of carbon actually means. And so, you know, when you go to a stop sign and there's a train car in front of you and you're sitting there for like 25 minutes waiting for this train car going by, if you filled the train car with, if you could take 40 billion tons of carbon and put it in a train car, the length of that train car would be around the Earth and the Moon 17 times. I mean, it's a big freaking number. So. But you're not here for this pep talk. You're here to understand why we're doing this and how you can contribute to making this better. Yes?
How many years will it take the train car to science?
That's excellent.
Chinese trains, 250 kilometers an hour.
It's an excellent question. So we're selling new missions on this, and in fact, usually a new mission is preceded by a group of experts getting together and arguing about science questions that the mission should address. And that's usually called a science definition team, and there's a 348-page document that describes what the science community thinks the PACE mission should look like. But if you distill it down to threshold science questions, you don't have to read these. But the point is that there are 7 substantial open ocean questions, 3 of which deal with understanding phytoplankton community composition. And so we're selling the mission based on the ability to do this. This is what the community wants. This is what Congress wants now. So we have to deliver upon this promise. And that's where you guys come in. My role here is just to give you a top-level 5,000-foot survey of all of the different approaches that exist. You can decide what you like, you can decide what you can improve upon, you can decide what you will never ever touch again. Leave that up to you. So NASA's invested in this. Believe it or not, they've put in 10 years worth of funding already to start this process. There's been a lot of convergent evolution where there are 50 railroad tracks, using the same analogy, 50 different trains going down, all doing things differently. For our part, we're trying to learn how to support this, but I'm not exactly sure how to do that yet, but it's an ongoing process. And this is really the reason I kept the slide in. There is so much more work to be done. And the reason for that is phytoplankton functional types and phytoplankton, or particle size, PSC, particle size, it doesn't matter. What's that?
Particle size class.
Class, thank you. It's the Wild West. And I love this cartoon because I get to actually come into an audience like you and sneak in the word beer. Nobody even notices. All right, so terminology before we jump into this. Particle size class. I should have gone one slide further. In this case, you're describing either phytoplankton or particles. In practice, these classes are divided up into 3, and they're prescribed by these size ranges. Okay? I'm not suggesting these are good. There is a whole community out there debating whether this is correct. And then you have a phytoplankton functional type. So think back to the lectures that Mary Jane and Ivona had given you before. What does function mean? It can mean many, many, many different things. But often in the context of these algorithms, it refers to class genish-ish type levels, diatom versus dinoflagellate, or some kind of role within the community, so the nitrogen fixer, calcifier, and so forth. But algorithms exist to do both of these, and they're not necessarily telling you the same thing. So to give you kind of an agnostic perspective from the salesman who is trying to give pep talks so that we can get a new satellite, the faithful and the skeptical are all around us. There are people who believe in this, that have made careers out of this, have become very, very successful. And then there are the rest of us who are like, this can't possibly work. The reason for that is this is absolutely pushing the limits of existing technology. I mean, with MODIS, with CWIFs, with VIIRs, with the spectral resolution of those, this is just pushing it to the limit. This is why we talk about hyperspectral emissions becoming the next step. Maybe with more wavelengths, we can start seeing different absorbing features of different communities. Many methods have been proposed. I'll talk about a bunch of them, but generally they fall into 2 classes. We talked about this morning, validation data for this. But like it or not, it's our future. It's already huge in our community. It's a huge science driver for our new NASA mission. And I'm going to walk through the methods and the issues. And in fact, we're going to start with some issues. So I think there are 3 reasons that validating a PFT or a PSC algorithm is going to be challenged. First, because of the increased degrees of separation between what the satellite algorithm is producing and what you're physically measuring in the field. Because there are a ton of methods to do this with the satellite and a ton of methods to do this in situ. And really, there hasn't been a lot of community convergence on this yet. And also think back to those horizontal, vertical, and temporal distribution plots that I showed you from the Arabian Sea. That's hard enough when you're just doing total chlorophyll. Imagine now trying to look for a tiny little patch, a little filament of something that's different than what's around it, and being able to relate what the satellite is seeing to what you physically measured there. It's really challenging. And largely it's because of the degrees of separation. One part of it is degrees of separation. So we can go into the field and we can measure remote sensing reflectance. The satellite can measure remote sensing reflectance if you believe the atmospheric correction. But you're measuring the same thing in the same units. You can measure chlorophyll in the field. You can measure inherent optical properties in the field. Satellite doesn't measure that, so you need a model to get to that. So you have 1 extra degree of separation here from here. Now when you're talking about phytoplankton functional type models, typically you're not measuring those unless you have a microscope out, or you can do it with flow cytobot and other things, but there's another step in the field often. There's usually a proxy assumption made between what you're measuring and your inference about particle size or PFTs. And then it's even worse for the satellite because you don't often, but you sometimes go from here to here, but mostly there's another immediate step. And in this case, every time you make one of these steps, every time this increased degree of separation increases, there's just so much more uncertainty because your uncertainties are propagating as you go from one to the other. Outline of the talk, diverse methods we'll go through. I am going to touch a little bit on sensitivities in the end, and this is a room full of people that should start thinking about this because not a lot of the algorithm developers actually do this. And then we'll talk a little bit about proxy data sets. So first, a word on measuring PFTs and PSCs in the field. I'm not sure this is comprehensive, but when I say a lot of methods exist, you know, they really do. And these all give you a different answer, or often give you a different answer, because they're measuring different things. And I don't know which one's the best. I don't know which one's the worst. I expect if we could all use microscopes and we could torture graduate students with microscopes in the bowels of ships in the Southern Ocean in the winter, we would. But most algorithms tend to use HPLC, pigment analyses. We'll talk about that a little bit more in detail next. Actually, let's talk about it now. Phytoplankton accessory pigments. So the reason we use HPLC is it's an abundant measurement. You can go back to these big databases and see a lot of HPLC measurements. So you're getting more temporal and spatial diversity in this. And the most common way, I'm sure you've all heard of chemtax, but in our circles, the most common way to relate HPLC pigments to a size class or to a particular phytoplankton in the water is through what's called diagnostic pigment analyses. And this is predicated on an assumption that dominant pigments can be used to infer dominance in what's actually in the water. And Mary Jane, you must have talked about this previously, earlier in the class. So it's not totally new material that. All right. But the general idea is that if you see a lot of fucoxanthin relative to all of the other accessory pigments, chances are it's a diatom in the water. Do you believe this? Do you believe this? You do believe it? Okay. And the same goes for the rest of these. And what you tend to look for in this case are, what you tend to calculate are ratios. So if you look at all of the pigments that you consider to be diagnostic of phytoplankton community structure, and you come up with the sum of all of those, and they're listed here, you would take ratios, so of things that represent different algae. So if there is a lot of fucoxanthin and there's a lot of peridinin relative to everything else there, chances are it's either a diatom or a dinoflagellate. So now we think it's probably a big guy. Yes?
Sort of a side question, but in general, we have the absorption spectra for individual treatments.
Yeah.
Although there still is a little bit of uncertainty in transferring the absorption spectra and hexane to an in situ absorption spectra in
Yeah.
And there was a paper that came out in Science or Nature.
Yeah.
That showed how changes can absorb the absorption right in the membrane. It's just just talking about the effect of chemistry on the absorption.
And I think you're sort of doing two steps here. You're asking first, is fucoxanthin would indicate a diatom presence? And diatoms not fucoxanthin, other things do.
Yeah.
Most diatoms do. But are all diatoms microplankton?
Yeah.
That's the second question, and that's a very different question
Mm-hmm.
than does fucoxanthin tell you you have diatoms? Fucoxanthin may tell you you have diatoms, but it doesn't necessarily tell you you have microplankton.
Right.
Because you can have very small diatoms.
Yep.
And the other thing is peridinin is not unique. Peridinin is not in all dinoflagellants.
Yeah.
And it's another
Exactly.
Fucoxanthin.
So now do you still believe it? You still do? Sweet. So I'm a satellite guy, so I'm going to spend most of this talk talking about satellite methods. So we're going to kind of leave field measurements here, but just coming back to this list, and then talking about a widely accepted method for no other reason that a ton of field data exists that support this method with all of the issues Colin and Mary Jane just talked about. There is a remarkable amount of work, if you have interest in this, in trying to understand if there's any convergence under these methods and how to do all of these things better. So cheerleading for you for a second. We're not going to talk about it much today, but there is a ton of work to be done here. A ton. Okay. It's too dark in here, so I'm going to turn the light on for a sec. We're going to pause. Before I tell you about all of the different things that we can try to do from space, if you were designing an algorithm from scratch and you knew nothing about anything about these existing algorithms, but you're really good in the field and you understand biology, what would you do? What would you use for your algorithm? How would you get, just if you pretend, I'm going to pretend for a second you've never read any of these papers. What would you do? What would you use? Would you use chlorophyll? Absorption? I actually want to hear, I'm not going on until I hear answers. Yeah. Okay, so you're saying you would use absorption? You would derive absorption and then, I'm not saying there's right or wrong. I just want to hear what, pretending for a second you don't know anything about these algorithms and you were starting to build your own algorithm. If you knew you needed to get to a particle size class, what optical proxies would you use?
Did you say particle size or functional size?
Either.
Okay.
Well, think about what you've learned in this class. What information that you think you can get out of a satellite would you use? Scatter? Okay.
Well, satellites looking at RS initially, so probably go to RS first, maybe.
Oh, you have to go to RS first, yep. So
Particle size.
to get to, yep. Backscatter? So, okay. All right. Well, we'll go through them. The answer is people have tried everything. They've tried all different products. And all of the different algorithms really end up into two different flavors. There are those that focus on abundance, and there are those that focus on spectra. So what I'm hearing from you is that you probably more are spectra. I've heard of absorption, I heard backscattering. But there are still those who are faithful with the abundance. And what I mean for this category is that you're exploiting what you've observed in the field, relationships between trophic status of the environment and the type of phytoplankton expected to be present. So if there is a lot of chlorophyll, for example, you're going to infer that there are big particles there. You can do the same with backscattering and absorption. The others, but it's basically saying a lot means one thing and a little means something else. Spectral methods exploit variations realized in spectral shape, whether it's RRS or absorption or backscattering, and how the variations in the spectral shape varies with community structure. So you're using unique optical signatures of whatever it is you're looking for, and it has to be unique. But if you see something that relates to a unique feature, then you can suggest that that thing is there. So getting back to my original question, there are varied inputs to all of these algorithms. Some use RRS straight up, some use chlorophyll, some use backscattering, some use absorption, some use phytoplankton absorption, and others use combinations. So my next few slides are going to provide the roadmap for the discussion of the rest of the algorithms. And in full disclosure, this came out of a phytoplankton ecology class I took with Mary Jane. Different kinds of data products. So the first thing you need to remember, and this gets back to a validation exercise being difficult as well, is that the different algorithms report different things. Some give you concentrations of accessory pigments, some give you size classes, and some try to describe the taxonomic community. So you have those that just take satellite measured radiances and go, well, some go in this direction, some go in that one. You have those that use only concentration of chlorophyll from the satellite. You have some that are entirely specific to absorption. You have some, where did it pop up, that are totally specific to backscattering. Yeah, you have some that use both. And then you have those that use some kind of mixture of radiances and derived IOPs. And this is a map. This roadmap is circa 2011, so there's been a few other things added. What I want you to do is to sit back. And well, before I say that, the colors represent whether it's an abundance algorithm in red or a spectral algorithm in green. But take a step back, and when I say it's the Wild West out there, this is why. There are a bunch of different approaches that take a bunch of different input parameters to get to a bunch of different products. It's not a bad thing. But you need to be an educated consumer. Which one are you going to pick? Which one answers your science questions? So as we walk through this, we'll start with abundance methods. Fundamental assumption of all abundance methods are that given a phytoplankton biomass defined by chlorophyll or IOPs covaries with the dominance of a fraction or of a particular size class or functional type. Does that make sense? If there's a lot of it there, it means something. If there's not a lot of it there, it means something else. We'll start with the most straightforward, which are that if I can get a good estimate of chlorophyll concentration from the satellite, I can tell you everything about the community in the water. Two examples here. The first is from Takahara. His algorithm, given a chlorophyll input, will give you an estimate of the percent of that chlorophyll for every size class and functional type in that given pixel. All he is assuming right now is that chlorophyll drives the entire system. The way he did this is he went into a database of radiances, chlorophyll, and HPLC, much like, I think he used Nomad actually, and he came up with empirical regressions for the concentration of chlorophyll versus the percent of that chlorophyll attributed to picoplankton, nanoplankton, microplankton, that's the top row, and then even farther down into subcomponents of each of these. The colors are just to show you that if you were to add these three up, it would result in that. I lost a point. Okay, anyway. So the algorithm is very, very simple. It is given a chlorophyll from the satellite, you plug it in to the algorithm or the expression for each of these lines, which is shown here. They're usually just hyperbolics or linear functions. And that's that. So if I have a chlorophyll, I can tell you a measurement of 0.1. I know that there is roughly 15% of that chlorophyll attributed to green algae. What do you think about an approach like that? Do you think chlorophyll is a unique descriptor of all of this? And remember, the other problem we're confounded by here is that what the satellite is seeing is an integrated value over some slug of water, too. So, of course, the near surface is dominating that, but you're not getting a... would you think you're getting any information about vertical structure here? Yeah?
So I have just a question. So in this case, you pretty much never guess that dinoflagellates are wrong?
Correct. No. Yep. I remember the point I wanted to make. These percent concentrations were derived using that HPLC diagnostic pigment analysis. They weren't measured. There was an optical proxy used. So these are the expressions if you're really into that, or I'll refer you back to the original paper. But the punchline is you can make maps that look pretty cool. So it's one way to do it. And please understand, I'm not trying to diminish any of this body of work here. I mean, the fact that people are thinking about this is really important, and Taka is an awesome guy. So this is not saying his work isn't good. This is just saying, hey, there's a lot of flavors, and you need to be skeptical. Second is from Julia. And this provides an estimate of the relative presence of 3 particle size classes, much like Taka's, given chlorophyll as input. And don't stare too hard at the table here, but what this work did was to use a range of chlorophyll. So you can see this top line just indicates different kinds of ranges, 0.12 to 0.2 concentration, and an estimate of mixed layer depth from some ancillary data source. to assign every pixel to a trophic category. So in the case if this is 0.2 to 0.03, so if the chlorophyll measured by the satellite was 0.25, it would be category S5, indicating some kind of and if mixed layer depth suggested that the water was stratified versus mixed, then this would be the trophic category that that pixel fell into. And what she did was to take a large database of water and come up with an average vertical profile for chlorophyll in their database for each of these trophic categories. So, stated another way, she empirically parameterized vertical profiles of PSCs for all 14 trophic levels assigned. And so what this is, where this is going is a little bit even further beyond what Taka did. She's saying, given her data set, that a chlorophyll that falls into a given range not only can be used to take an estimate of the vertical structure of that water, which we were just talking about maybe really isn't viable. I mean, it might be. Their data are very good. And in the global open ocean, perhaps this is okay. But now we're taking that extra leap. We're saying that that one estimate from the satellite can tell me not just what's in the water, what size of it's in the water, but how it varies as a function of depth. And they took it even further. They related these distributions of vertical distributions of nanoplankton to productivity, vertical distributions of productivity by phytoplankton. And in the end, you get maps. So estimates of marine productivity, vertically integrated marine productivity from an estimate of chlorophyll made by the satellite at the surface. Any questions on chlorophyll-based methods? All right, let's move on to absorption-based methods. We'll start with another body of work by Taka. He assigns a dominant size class to each pixel, this time using absorption. And in this case, it's absorption measured in the field, phytoplankton absorption, with the premise that the slope from the blue to green, so in his case, 443 to 510, and the magnitude of 443 can be used in combination to infer a particle size class. So this starts getting, it combines pigment packaging with particle size. So in this case, again, it's using a threshold. So we have multiple algorithms, as Colin has described, to invert remote sensing reflectances to A phi. But then you use the shape of the derived A phi to get an idea about the particle size class. And the way it works is that typically it's a micro phytoplankton when A phi is greater than one number, it's pico when A phi is less than one number, and it's nano otherwise. Now, how many different flavors of inherent optical property model did Colin and Kurt talk about this last week? I wasn't here. Of the IOP models, how many different flavors of them? All right, but you had an exercise where you were playing with the inversion and all of that stuff. All right, so those models are a little tricky. Now, so you pick your favorite and you assign a threshold to it. And so there's some uncertainty here, even though this is more optics-based. It really depends on what model you pick, what inversion model you pick. How do you get to A phi? So there's that extra step to be aware of. All right, that's all I have to say about abundance methods for now. We're going to go on to spectral methods. Again, you're exploiting variations from the spectral shape of RRS or IOPs with community structure. The nice thing about these is that you can detect different functional types and size classes with a common total biomass. So as you've probably learned in your hydrolyte exercises and so forth, a given chlorophyll can have a bunch of different RRSs associated with it. So that's one of the ambiguity problems that I'm sure Colin talked about, that when you're going backwards from RRS into IOPs, different combinations of IOPs can give you the same RRS. When you go from IOPs forward, it's an exact solution. When you go back, there are multiple solutions. And this tries to combat that. And it works when your PFTs or your particle size classes have contrasting optical signatures. So of course, if they look the same, this doesn't work. Unfortunately, this makes the assumption that you can assign one spectral shape to a diatom and have it be true in all places for all times. Is that what you've seen this week? Does a diatom always look like a diatom? Can the same diatom look different later in the day? Or depending on the temperature or the nutrients? I'm not seeing any heads nodding or shaking. Do I need to turn the light on again? So, it's my last talk. Come on, humor me. Okay. They can all look different. So one of the limitations of this is you're assuming your optical signature is applicable for all waters at all times. In its most simplest form, you can proceed exactly like you do for the chlorophyll algorithm, standard chlorophyll, where you take band ratios of radiances, and instead of relating them just to chlorophyll, you can relate them to anything you want. So Jiaju Pan did this with one of my colleagues, Goddard, and it uses band ratios to give you an estimate of phytoplankton accessory pigment concentration for every pixel. And the way it's done, again, is really just regressing wavelengths of remote sensing reflectance to an accessory pigment from HPLC seen in the water. They only suggested it worked in certain places. But you can do it, and if you think back to the slug of chlorophyll data in the algorithm from my last talk, where we were looking at different regional things, the blue and the gray graphs, then what I could tell you is that this is a lot more diverse in this direction than those algorithms, not surprisingly. So that is a real straightforward method. Excuse me. There are a couple of others we'll go through really quickly. Ajit has one. Yep. Oh, sure.
Is that log 10 or
Log 10. Ajit was particularly interested in trying to detect trichodesmian blooms using CWIFs, and he only used radiances in the input, and a lot of this was visual inspection. He knew where there was tricho, either through conversations with people in the area or field data, and he looked at the imagery and he just assigned thresholds to the radiance values, that for the pixels he knew there were tricho, these conditions were met. So 490 was above a certain threshold, and 490 was greater in magnitude than everything else, basically meaning that 490 was the peak of the reflectance spectra, and so forth. All of these thresholds are basically looking for a certain RRS spectral shape. So he looked at a bunch of imagery, he created these thresholds, and then he assigned it to every other pixel in all of the imagery. Also pretty straightforward. This is Severin Alvain's approach, which is part of a really substantial group of papers now. It's nice. Provides estimate of dominant phytoplankton functional type for each pixel. It's nice in the sense that they've pushed it forward and refined it. The way it works is to look for anomalies in remote sensing reflectances. And so they assembled in a huge database of CWIFS imagery, big global maps. And they found out for particular chlorophyll bins what the average, this is effectively remote sensing reflectance, normalized water leaving radiance spectra for that. So in practice, what that means is that if you look at the big global map and you take the average of all pixels that had chlorophyll greater than 1, the average spectra looks something like that, for example. And so they retain all of this information, and then when they look at new imagery, they know the chlorophyll value from the CWIFs, or from the algorithm itself. If it, for whatever range it falls in, they go back to their database and they get this average spectra, and then they take the spectra measured at the time of observation and subtract it. And so what these are plots of are residuals, differences in the average NLW value seen over all globe with what's actually being seen at the time of a new observation. And what they're suggesting is that the shape of these residuals relates to the kind of phytoplankton in the water. And they did this for 4 classes. What are they in here? Haptophytes up here, Prochlorococcus over there, Synechococcus-like class here, and diatoms over there. Is that clear? I'm just kind of grumbling. My throat was grumbling at the time. Do we need to do jump-in jacks or something? All right. Another absorption method, Ariacciati. Estimate the relative fraction of two different particle size classes for each pixel. The way this operates is that you grab a phi spectrally from the inversion algorithm of your choice. That is here. You have lookup tables of normalized absorption spectra for picoplankton and for microplankton. So you're just suggesting these are typical A-phi shapes for those two classes. And what you do is you run an inversion to find out the magnitudes of each of these. You find the magnitude of the contribution of each of these that would be required to reproduce what you're seeing from the satellite. So this is very similar to an inversion algorithm. You're prescribing two spectral shapes, you have a measurement, and you need to find the best fit. What combination of these two gives you what you're seeing originally? This is a nod to you, Miss Chase. Allie has a nice method as well. Do you want to talk about it? You're the author. No? You should have a shot. It's good work.
So I used a whole bunch of ACS absorption spectra that was measured to be like an inline system. And I used HPLC data collected at the same time that the ACS was running. And I used a series of functions, those are all the blue curves there, to find the best combination of those functions that represents the absorption spectrum. And then I compared the magnitudes of those individual Gaussian peaks to HPLC pigments. And the idea is that those individual curves represent absorption by different pigments. So some of them are the same because if you remember like the chlorophyll A, B, and C spectra, they have peaks of the blue and the red. So in some cases there are like 3 of the peaks represent chlorophyll A, and B, or also some of the other carotenoid pigments absorb really similarly, so I had to clump them together. So after I validated looking at the HPLC pigments, then I went back and applied the method to all the ACS spectra that I had, which is like hundreds of thousands from Tara, and used 4 other data sets from CBAS.
I didn't mean to put you on the spot. I'm sorry for putting you on the spot, but.
Yeah, so the blue functions, I did a little iterative thing to see which would be the best center of each location, but they are based on like real pigment absorptions. And so then all the functions have a fixed center wavelength and a fixed width. And then and so the NAP it does have a fixed slope. You can see in that case it's really super low. Yeah, it's an exponential, that line along the bottom. Yeah. It was for a lot of ideas, so it was a lot of overlap with NAP. Yeah, so it starts before like the least squares inversion, all the Gaussians have like an equal magnitude, and then they come out like that.
Thanks, Sally.
Yeah.
Okay. On to the backscattering methods. This is from T.O. Kostadinov out of James's lab. This uses backscattering as input, and it takes an algorithm from Hubert, Loisel, and Darius to generate a satellite estimate of the backscattering spectral slope. Using that spectral slope from that algorithm, TO estimates the relative fraction of 3 PSCs for each pixel. Okay, so this proceeded with me theory, which you'll learn about next week. Use a forward me model run, and what you're looking at here for different particle size distribution, Young's slopes, came up with what a normalized backscattering spectrum should look like. So wavelength here, backscattering on this axis. And you can see that the backscattering spectral slope changes with particle size distribution using me theory. And so the general idea is that you calculate the backscattering spectral slope using the satellite, and then from that you can get all of the different parameters required to reconstruct the particle size distribution, a full particle size distribution. And once you've done that, you can start creating maps of that particle size distribution Young's slope. That's what you see here. With that information, you can take it further now. If you have the full spectral slope and you divide it up into the bins that you care about that represent pico, nano, and micro phytoplankton, you can use it to infer distributions of nano-sized particles, pico-sized particles, and so forth. And they went so far as to try to relate these into volume, not just concentrations, but also volumes. So it requires an assumption that all these particles follow me theory, but and that all of the algorithms work, because there's a lot of intermediate stuff, but it's innovative. Yes?
Given the very coarse spinning they're doing and all of the assumptions that go into it, it seems like it would be more effective or just more reasonable to make a map instead that had like 3 different colors on it for which regions were dominated by which.
Yeah.
Hey, do they have a map like that in this paper?
No.
Is this really
No. No. What's that? Did you do it in his later paper? Where I was just indicating the dominant ones? Yeah. I mean, I absolutely agree with you. But
Using a unit distribution with me theory, one of the things that ends up happening is this base function is constantly spectral. And so,
yeah. So come back to this next week after you've done the me lab. And now that you've all looked at phytoplankton under the microscope, are they all spherical, homogeneous, no coatings? What's that? Yeah, don't exactly. All right, on to some of Colin's work. And Manuel's work, and Colin and I spent a lot of time on this the past couple of years as well. So this is an inversion modeling exercise that's similar to what you've already discussed last week. But in this case, rather than solving for a single A phi, you're solving for multiple A phi. There was also another nice paper, over 10 years old now, to get to slope of BMC. The general operation of this is and you know this from your inversion algorithm modeling exercise, but you can expand A into an infinite number of some components of A. And all that's really happening in these algorithms is that instead of assigning one spectral slope for phytoplankton and absorption, you're assigning multiple ones. And then you proceed with the inversion exactly the same way, where now you're solving for the magnitude of these different phytoplankton communities, and then you can use that to infer contributions to absorption, contributions to total chlorophyll, all sorts of things. And this is just an example of the differences for different communities. For data, this is from the Benguela, right? Yeah. Okay. All right, so any questions? That's kind of my very quick survey of all of the different kinds of approaches. You had a question. Okay.
Well, I was just going to say that one of the points that I hope that we made when we talked about this is that if you're trying to separate out optical features that having to do with different phytoplankton, and it doesn't matter which model it is, because they're all kind of pinning in on different pigment differences. They only work when the differences in pigmentation give rise to differences in absorption. And give rise to differences in spectral reflectance.
Right.
So, it works great in Venezuela where you have monospecific balloons and nothing else in the water. The only thing that's giving rise to the variability in reflectance is phytoplankton absorption by different species. And so you can tell the difference because nothing's driving it.
Yeah.
But if you're in a situation where the PFT, would be its size, would be its absorption, isn't changing your reflectance, you can't get that information back out. And I think that that's where a lot of modeling has really gone astray, is not thinking about the process in a forward sense before you go back in the reverse sense. And so,
No.
you just got to make sure that what's causing the optical variability in your system is what you're trying to go after. Otherwise, you're just modeling.
Yeah. Which is why it's really hard to apply these globally and blindly.
I wonder, because I don't really pay attention to this too much. We had hyperspectral instruments now for so many years.
Yeah.
Has anybody really done a validation where they took hyperspectral remote sensing reflections and did something with it to get PFDs? I haven't seen
That's like
anything.
half of our PhD theses.
Yeah. Yeah, I mean, there's been one-offs, but they've been done very regionally. They've been done very regionally.
Yeah.
So, I mean, like, it worked for Benguela when Colin did this. It did not work great in the Arabian Sea when we worked together. I mean, that's the papers we ended up writing were, hey, this is...
So, I mean, if I was a NASA program, that were higher than the program manager,
Yeah.
and you're proposing something like this, I want to see some field validation.
This is why we're not inviting you to the meetings. Cheerlead. No.
But
Yeah.
I think there's enough, with some of the airborne sensors, there's a lot of garbage out there. And it has not been adequately corrected for glint or for all the other atmospheric problems. And so, those have been kind of stopped in their tracks. And when they do the inversions on well-corrected hyperspectral data, what they're validating with, it gets back to that whole list of, are you validating it relative to absorption, which is what you should probably validate it to,
Yeah.
the first step. But then, are you validating it by product? And each of these test cases, they've been validating two different things. And so then my question, Jeremy, I talked about ad nauseam, is like, if you're going to put validating data into CBAS, what's it going to be? Is it going to be someone's microscopic counts from one depth, from one station within a pixel? And where was that sample collected relative to the validation, relative to the optical depth? Is it pigments? Is it list data with size classes? I mean, what is going to be the standard? And that's the problem, is that there isn't a standard yet. And I think that's
Not even common
biggest-
units yet.
Not even common units.
Yeah.
That's the biggest problem, is that we have all these people running off doing all these empirical algorithms and measuring different shapes of reflectance and calling it diatoms, but what are you validating it against? Like, oh, well, there's usually diatoms in this region this time of year, so that's good enough. And that's just not good enough.
Yeah. And I'll show you a couple slides on that.
Climatology, or it's violating the rule of using the same data that was used to construct.
Right.
Yes.
Yeah, exactly. Shamefully happens a lot.
Absolutely, and that's something to really look at, is the data that goes in. And even if they take some of their data and they randomly select certain stations out, it's not independent. If you look here on Tuesday at 10 and Tuesday at 11, you're like, well, I'm sure not the 10 o'clock data, that's going to be my test. Like 10 o'clock and 11 o'clock are not really independent samples. So it's a problem, and Ken's right.
Yeah.
You don't deserve the satellite.
You want this without PACE, funding goes away for research and vicarious calibration systems and cruises and stuff. So
As the justification to get ourselves in gear to get the right validation approach.
Right.
And start really hammering the models. They all need to be really examined carefully, all of them.
Yeah. All right, so I'm going to turn the lights on again, and I'm going to ask you 2 questions just to break this up a little. I'm going to ask you the same question I asked you before. Now that you've seen kind of a survey of what's done, which method would you pick if you had a gun to your head now and had to decide? None isn't a real answer. Which one? So that's a class. Which one of the spectral shapes? Okay.
We have, sort of following along the lines of when we were learning about the inversion algorithms, they all seem to converge on one stylistic way of doing things. Like, how about, okay, we had all these empirical measurements kind of branching us out because we had no standard, but if we had a situation where we had a calibration, would we converge to that and then figure out how to calibrate that method?
Anybody else?
Has there been any, this isn't an answer, but has there been one that works a couple of different methods? Like for example, if you have, if you're looking at spectral shape, but then you're taking information or a different, I guess, empirically derived ones. A lot of them seem to be very specific, in some ways specific. They're not, they're all specific for identifying things well, but in the methodology it seems specific to use one.
I'm not aware of too many, but it's intriguing.
Like diatomic buttons purely as a function of chlorophyll buttons rather than like temperature, like information that is known about the water.
Well, okay, so that leads to my second question. All of these are really self-contained ocean color. The only information you have is ocean color. What other, building on what you were asking, what other information would we want to do this better? Temperature was one. Yeah. What else? And I could turn that around the other way. If you were building a satellite observatory, what other kinds of instruments might you add to it to complement just an ocean color instrument? Any ideas? Well, PACE right now doesn't measure temperature, so you would want a thermal instrument on it. Doesn't measure salinity. How about LiDAR? Could you get some more information from LiDAR? What would LiDAR give you? Could. Yeah. Yeah, well, so let's build on that. Rather than bathymetry, what else could we learn from LiDAR? So let's just say the signal doesn't penetrate all the way to the bottom. What's that? Probably do mixed layer depth. You could start getting backscattering distributions, get a little bit. You can get more information about vertical resolution. Okay. And then there's another, one of the things that we're talking about now is polarimetry. So knowing what you know about volume, scattering function, and particles, if we were able to view the same pixel from a bunch of different angles, what else could we learn? You can start getting a volume scattering. So there's a lot of other information out there that, in my opinion, to evolve this, it can't be done only in isolation. We need to get better about bringing in other information and using that. So, all right, between me and lunch again. Yeah, that would help too. All right. This won't take too long, and then we can break for lunch. But a quick note on sensitivities, because this is one of my personal pet peeves, is that a lot of these algorithms are developed, but then nobody perturbs the system to find out how good they are if given varied inputs. So we already talked about things like you have to get a phi for some of these models from somewhere. You know, how different is your answer if you picked QSA versus GSM versus whatever to get to a phi? If you're taking a chlorophyll measurement, how good does your chlorophyll measurement have to be? If it's, I mean, our goal is to get chlorophyll within 35% of what you see in the field. So what if you're 30% off? How does it change your downstream answer? And this just basically says that. So my curiosity and my challenge to you as we go forward with this are how sensitive are the abundance methods to uncertainties in your derived intermediate products, and how sensitive are the spectral methods to uncertainties, not only in the magnitude of these, but in varying spectral shape. And I just have 2 quick examples. This is a complicated plot, I'm sorry, but I think it tells a good story if we walk very slowly through it. Maximum band ratio on the x-axis. So this is your RRS ratio. Chlorophyll concentration on this left axis. And so this black line is the curve for the OC4 empirical algorithm. All right? If you were to try to divide the algorithm up into rough trophic levels, the boundaries are, the eutrophic would be this dash, everything over here, mesotrophic would be everything over here, and oligotrophic would be over here. And the boundaries here are chlorophyll of like 0.1 versus chlorophyll of 1 and so forth. If to create these different color plots, if I change my maximum band ratio by some prescribed percentage, either adding or subtracting 2%, adding or subtracting 5%, or adding or subtracting 10%. So I'm just moving the value along this axis. How much different would my chlorophyll be? And that's what this other side of the axis is. So if my maximum band ratio was wrong by positive 2%, right around this region, my chlorophyll is going to be off by roughly 8%. Here, if my maximum band ratio is off by 10% in really, really clear water, I can have differences of up to 40%. And so when you're thinking back to all of the talks that we've had on calibration of the ocean color instrument in space, I mean, it doesn't seem too unlikely to me that the ratio of two bands, especially early in emission, might be off by 1 or 2%. I mean, that's a small number. But even 1 or 2% in really, really clear water means your chlorophyll can be off by an order of 15%. How does how does an uncertainty of 15% in your derived chlorophyll factor into some of these PFT models? I don't know. I don't think that's been explored yet. And then one other example is for the inversion algorithms, and this comes from kind of a community-derived paper, is given one run of your inversion model, let's just call it a standard run, a default configuration, and you were to change your backscattering spectral slope by plus or minus 30%, or your CDOM spectral slope by plus or minus 30%, or you were to wrong in your, in this case, your A phi by plus or minus 30%. What is the difference in the derived products you're getting relative to the first run? And so what this is showing that your choice in how you parameterize your model can translate to uncertainties anywhere from less than 1% to 30%. And then these are just arbitrary choices sometimes based on what you think you know is happening there. And even your choice of how you do the inversion, whether you're doing a nonlinear fit or a matrix fit, can give you changes from 2 to 7%. How does this propagate into your uncertainty of your phytoplankton size class? I don't believe that's been explored either. So that's my challenge to you all. Two other things on this. If you want to learn more about this, there are a couple of good resources now run by the IOCCG. They have, is good fair, Colin? I said good resources. There are resources. So this is an encyclopedia of similar material to what I presented in this talk. They've had a couple of workshops and have written things down. The references are here if you're interested. What I found, I was asked to give a talk there about the difficulty in doing the validation, and I, before the meeting, threw this out to them as a survey, and I asked them, I asked probably 30 people, what are the 3 biggest problems you faced in your algorithm development and validation activities? 5 of them were kind enough to respond, and this is the number of people who voted for each thing, but the responses that I accumulated. But 5 out of 5 said, I am limited by my in situ data set. 2 of them were forward thinking enough to realize that there are scale issues. And then the rest, satellite uncertainties to algorithm inputs. This is what we just talked about. Detectability, we didn't cover that here. But again, what if, if you have layers of different types, how do you separate those if you're only looking at an integrated value? If there is a huge bloom of something that's different than what's at the surface, deeper,